Yeah, it is. Okay, so this was made by George Cleese last year. He took my 87.
It does not mention other names.
Because George Cleese made the whole thing. And without any help from me really even, but I mean I did tell them like do these 87 things and he just did it. Okay, but there's some repetition because the two groups working independently. So, okay, so going very fast. Blah, 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 calculus, Archimedes makes it rigorous, his methods were tedious. Good. Finally, Epsilon-delta proofs will save us. Fortunately you guys already know all this, so I don't need to like teach it. But basically, the limit at a point C is L if we can get within epsilon of L by getting within delta of C. And what's important is if we are going to formalize this, we are of course going to formalize it in terms of something. And note what it is that we have decided is more secure than geometry. Well, it's basically like numbers, man. Numbers, inequalities, absolute values, quantifiers, stuff like this. This becomes like the new math, the mathematics of like numbers. And, okay, where are we? All right, so this is, George kind of reteaches the whole Epsilon-delta. I don't feel like we need to do all this. Oh, should we do like a 2-minute, just like, does everyone remember how to do these?
Yes.
Okay, let's take 3 minutes. So suppose you want to take the limit as x approaches 4 of 5x minus 7. Well, that's 13. And how are you supposed to think about this? Well, you have like a, what are we doing? 13. So you have like a line, 5x minus 7. And by the time you get to 4, you're up here at 13. And it looks something like that or whatever. And yeah, I agree, getting really close to 13. What does it mean to be so close to 13? VT, can I get a red and a blue marker? It means that for any possible, one at a time.
That was a little low.
Good. For any possible epsilon challenge, so no matter how close to 13 you want me to get, I can get sufficiently close to 4 that within the interval 4 minus delta, 4 plus delta, all of the values of my function lie between 13 minus epsilon and 13 plus epsilon. And the way we always did these was to do a discovery phase. Again, I think I taught calculus to everyone in this room. You would try to discover the delta that works by starting with the thing that you're trying to prove. You start with the difference between the function and 13 being less than the challenge number. And then you just kind of go 5x minus 7 minus 13 is less than epsilon. And you get 5x minus 20. And then that means you can now pull this move where you're like, I don't know, doing some math. And then, oh, I see. It appears that if x minus 4 is between negative epsilon over 5 and epsilon over 5, then everything's going to work out. So therefore, what x values do I need to restrict myself to? 4 minus epsilon over 5 and 4 plus epsilon over 5. And therefore, it seems that I should set delta to be epsilon over 5. Is the conclusion of discovery phase. And now you do the actual proof. The actual proof says for all epsilon, we need to take an arbitrary epsilon. So take epsilon greater than 0. What do I do immediately? I respond with my delta being 1/5 of that number. Then I attempt to prove that for all x, if I am close enough to 4, specifically within epsilon over 5, then my function will be sufficiently close to 13. And it all just like works out because we picked the right delta in discovery phase. So you assume that the absolute value of x minus 4 is less than epsilon over 5. You multiply by 5, you stick it back in, you kind of separate, and you just like get it. Cool? Okay, good. That was a 4-minute recap of Epsilon-delta proofs. But as this is a logic class and everything, what's actually happening here are some quite delicate quantifier moves. So you guessed it. What are we going to do right now?
Fitch-style proof.
Let's go. Take out a piece of paper. We will do a Fitch-style epsilon-delta proof. That's hot. All right. Yeah. Good. All right. What's step 1? Oh, should I state the thing that we're actually trying to prove?
Yeah.
Okay. Goal, prove the following from no premises. For all epsilon, okay, we don't really have a greater than 0. So when someone says for all epsilon greater than 0, what do they really mean?
What? Epsilon's greater than 0 and.
Epsilon's greater than 0 and there exists what is this?
I think it's an if-then, right? For all epsilon, when people say for all epsilon greater than 0, they mean for any epsilon which is greater than 0.
Yeah.
Then
There exists
Whatever.
Epsilon
Then
is
there-
greater than 0 implies versus
then-
epsilon is greater than 0 and is exactly equivalent because negative epsilon, no one cares about negative epsilon. So those things are just
good conversation. So there is a delta such that, what's true about this delta? It's greater than 0. And
something implies something else.
for all x,
If 0 is less.
I guess we're doing, what are we doing there?
Right?
4?
Yeah.
Is less than delta then absolute value f of x minus 13.
Don't write f of x, right? Especially when it
Yeah, either way, whatever, either way. Is less than epsilon, zon, 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 zon. All right, go.
is. We don't even have arithmetic.
Oh yeah, we're gonna have to invent that as we go.
Let's just repeatedly use the transfer. Yeah.
So, step 1.
Take epsilon.
A or whatever. E. Let's use Roman E so it's like clear what things are.
Let's just call it epsilon.
That's
Take arbitrary.
more confusing to me, but okay.
Do you think? Oh, I don't know. Okay.
Seems more
That's more confusing.
I'm gonna write it as.
Let's use a backward
You can use
E for
the other type of epsilon.
No, that's not a good
Why not
idea.
just use
Backwards up.
like Latin E, and then it's then the
Use like a
Latin
symbol for
the
element in.
take.
All right, this guy wants to use Latin, so we will use.
Whatever Roman, whatever.
Okay, E. Good. All right, take arbitrary E.
Suppose e greater than 0.
Yeah. Find 1.
So we're using the same function from this
Yeah.
one?
So we did all the like thinking already. Now we just have to do rigor.
Can we like take d, suppose d equals epsilon over 5?
I don't even
No,
think
it's
I
not
need to
defined
do
in
that.
I think you could just do it straight up with epsilon over 5, right?
Yeah, you just start talking about epsilon over 5.
So like.
You have
epsilon-
anything you'd like to say about epsilon
so
over
like
5?
Epsilon over 5 is greater than 0.
Yeah. Yeah. E over 5 is positive. Fact. Okay, reason? I don't know. I'm just going to be like arithmetic.
Division property.
1. Yeah, I'm not going to get into that. I'm just going to be like, math. 1. Okay, but everyone agrees that line 2 follows from line 1. Okay, good.
Take an arbitrary.
Now take an
Then
arbitrary
take
x.
x, yeah.
Yeah. Do you guys see what they're doing? They think that they found their delta. Their delta is going to be epsilon over 5, right? So they showed that it has this. Now we need to prove this. So now what do you want to do? What do you want to call your variable?
I don't know. Some
Curly X.
Can I just call it x?
Curly x.
Is that going to bother you guys? Can
No,
I
it
just...
bothers me more to be x.
How about 1?
So it should be something that's not x.
QOZ.
Make it Y.
Make it Y.
Wait,
Chi is
like
Okay.
That's so weird. You're really not gonna let me just call it X?
I mean, you can.
I feel like that's
I will be chi.
Alright, good. Alright, what's true about that X?
Well, let's assume that 0 is less than x minus 4 is less than epsilon over 5.
Yeah, good. Now we need to prove this conditional. So it's now like take x minus 4 is less than epsilon over 5. And we should hope to prove
E, actually.
this, right? Oh yeah, E.
Yeah.
Okay.
Should that be like two
Multiply through
lines
by
that are,
Zero.
it's greater than 0 and it's less than 0?
Yeah, okay,
Oh,
that
that's
seems
true,
like,
that's true.
it seems like a good thing to do. So like, could you, like, I mean, I'm just kind of like making this up. I mean, not really, I've done this before, but, so, like reason, I don't know, definition of like, definition of compound inequality or something like that, line 3. All right.
Then to do math and assert that the thing holds.
Yeah, well, first of all, it's only the right one that I really need to use, yeah?
Well, then what is the second
Feel the rigor. Feel the rigor. Okay, now what?
Multiply by 5.
Multiply by 5, yeah, in that voice too. And then just like reason, like, math, line 5.
Yeah.
Let's not get into the details. What now?
Put the 5 into the absolute value.
Put the 5 into the absolute value. Woo! Math, 6.
Good.
Like now just like,
plug in
Now
how
just
like
like
do
what is
some-
f of x?
yeah, what is f(x)? It's like 5x minus 7,
5x
right?
minus 7.
So this is really like 5x minus 7 minus 13. Yeah, we could have done this all in one step. Is less than e. Reason, like math.
I'm learning so much rigor.
7. Rigor. Okay, and
Love this class.
like did we can we just call this f because it's like better. So I don't have to write as much. Okay. So reason, like, I don't know, like definition of f of x or something. Line 8. Okay. So I succeeded in proving the conditional, yeah?
Pop out.
Yeah. 10. All right. We have just shown. Dun, 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 dun.